The second lesson in topic 11 is titled Normal Distribution. In this lesson, we'll look at comparing data with standard deviation and mean. We'll look at things like percentile rank, and we'll find z-scores. The definition for normal distribution is over on the right-hand side. It says, in many large collections of data, scores tend to be symmetrical. About a single value that corresponds to the mean, median, and mode. That symmetry can be represented with what's called a normal curve. So a normal curve is what represents what's called normal distribution. For example, if we looked at the ACT scores, say in Orono, and then we looked at the ACT scores in Minnesota, and then possibly the ACT scores in the United States, what would end up happening is the mean, median, and mode would all kind of revolve around the center of that curve, or the middle. And then you have little dashes at the bottom, and that'll represent a range of scores within that central location. Now, the values that we'll look at to help determine the division between this, or within this curve, are the mean, which we represent with an X and a bar on the top, and the standard deviation. And the nice thing about representing normal curves is standard deviation will be given to us. We won't have to calculate it in this lesson. I'm sure we can all appreciate that. Now, within this curve, there are specific divisions that represent percentages of the entire set of data. So what I'm going to do is divvy this up for you, and then we'll talk about those percentages. So what I did was where those dash marks are at the bottom is I just kind of drew dashed lines all the way up to the top of the curve. And hopefully you recognize there's a little bit of symmetry in here. I'm actually going to kind of redo this one. I don't really like where that's going. So let's see if I can make that, oops, a different color. That's fun. Let's see if I can make that any better. There we go. Kind of goes right through that middle. Now within this normal curve that represents a large group of data or collection of data, the middle of this curve, right smack dab in the middle, is where the average of your data will be. I'm just struggling writing this out today. There we go. That's where the average of your data will be. And then as you move to the right and to the left, the average amount of the data is going to increase in data point by a standard deviation. So if you take the average of a group of data and you add one standard deviation, you're at this dash mark. If you add 2 standard deviations, you're at that second dash mark. And then right here, you would be at 3 standard deviations, which is pretty far away. Notice the percentage of data and that portion of the curve is very small. Now, if we go in the other direction, you would be subtracting a standard deviation value. So maybe the average on the ACT is a certain number, and then the standard deviation, there are a percentage of values to the left that would be lower by 1 standard deviation for that dash mark, by 2 standard deviations, and then by 3 standard deviations. So it's very symmetrical with those dashes at the bottom. Now the percentages you're going to want to know, obviously closer to the average, the curve is taller. Those are higher percentages. So I'm going to write them vertical. Let's see. So right where the standard deviation bar is, to the right of that, in this curve, there are 34.1% of all data values lie in that portion of the curve. And it's symmetrical, therefore 34.1% of the data values fall on the other side as well. As you go to the right and to the left beyond that 1 standard deviation, notice the values or the curve gets smaller. Therefore, the percentages are smaller as well. To the right in that second column, only 13.6% of data fits there. And that same rule applies on the left-hand side. And you don't have to write this kind of vertical like I'm writing it. Write it however works best for you to see in those columns. As we continue on, that next column is super teeny tiny. Only 2.2% of data values would fall within that second to third standard deviation. Same rule on that left-hand side. And then at the very end, oops, that's a percentage. Oh boy, that should have been a percentage. Let's see if I can fix that here. Sorry. At the very end on the left, wow, okay, we're just gonna start over. We're just gonna do the whole percentage over again. There we go. At the very end, there's a small, very slight percentage of values to the right of 3 standard deviations. It's 0.1%. And over here on that left-hand side, 0.1%. Those would be where your outliers would kind of hang out. It's not very likely a value is that far away from the average. These percentages are going to be consistent throughout our work today. Let's apply this. It says a set of normally distributed data has a mean of 26, that would be our x with a bar across the top, and a standard deviation value of 4. That's that little O with the loop through it. It says model this with a normal curve. We have that template over on the right. So just draw a line across the bottom if you're putting this on notebook paper and try to create a curve that looks similar to this. We'll just do the best we can. Now what we'll do with those tick marks at the bottom is we'll actually write numbers that represent our data point value kind of ranges. In the middle, we know that our average is going to go right at that center number, that center dash mark. So we'll put 26 right there. If I count to the right, what I'm going to do is I'm going to add my standard deviation to that. And the standard deviation is 4. Therefore, over to the right, I'm just going to increase by adding 4 each time. The next dash mark would be at 30. The next dash mark would be at 34. And then all the way to the edge, 3 standard deviations away would be at 38. And those would be those not very likely values. Now on the other side, if I subtract 4, the first dash mark to the left of 26 would be down to 22. And then we drop down to 18. 3 standard deviations away on the left would drop down to 14. So looking at this normal curve, we have values that range from data points of 14 all the way up to 38. Using those percentages up above, we can look at where the data lies within this curve. Let's take a look at the first example. What percentage of the total curve lies between 18 and 30? So as we look at this, between 18 and 30, I want all the data values within those 2 numbers. What percentage would lie within that set? Well, from the average of 26, on that left-hand side, we know that's 34.1%. To the left is also 34.1%. And to the left of that one is 13.6%. That would be all the data from here all the way over to here. To figure out the percentage of that, we just add them all together. 13.6 plus 34.1 plus 34.1. The total percentage of values that lie within that range would be 81.8% of all the data values. That's what lies within the numbers of either the range of 18 to 30. Let's try another one. Example or part C. It says, what percentage of values are greater than 22? So if we look at greater than 22, pick a different color here. So what percentage again? Greater than 22. That means from 22 over to the right. So we'd have our 34.1, 34.1, 13.6, 2.2, and our 0.1. If we add all those values together, our total percentage, let's see, 34.1 plus 34.1 plus 13.6 plus 2.2 plus 0.1 would be 84.1%. Those would be all the data values that are greater than 22. For our last example, we're going to go to that definition on the left, percentile rank. If you've ever seen a standardized test score, you get your percentage as what's called a percentile rank. So I'm just going to make this a little bit smaller right here. Let's see. All right, so I'm going to zoom over so we can get, the percentile rank in there. When you're asked to find percentile rank, what you're looking for is the whole number percent up to a data point. So here's what I mean by that. If you have a score like, let's say 94.2%, you exclude the decimal portion and your rank would be 94. So the percentile rank is the 94th percentile. Even if you have a percentage with a decimal that's greater than 0.5, like 94.9% would still have a rank of the 94th percentile. Now, the only time that this rule doesn't apply is if your percentage is lower than 1. If you had 0.4%, we can't have a percentile rank of 0. This would mean that your rank is the first percentile. Even if you had 1.7%, that would also fall in the first percentile category. Keeping that in mind, let's finish example D, or part D. What percentile, hang on, time out. Gotta get a color in here. What percentile rank does a value of 30 have? So if we look over at our normal distribution, a percentile rank of 30 is the percentage that's up to that score of 30. So we would want to have everything up to that point. If we add all of the columns, the 34.1, the 34.1, this 13.6, the 2.2, and the 0.1, that would be just the same percentage as part C. That would be 84.1%, but then the percentile rank is simply the 84th percentile. Okay, let's try an application question. It says the blood cholesterol reading for a group of women are normally distributed with a mean of 172 and a standard deviation of 14. So it says create a normal curve to represent the data. Pause the video and see if you can start with 172 in the middle and create the numbers at each of the dash marks for this normal curve. Then press play and we'll work through the rest of the problems. Do your numbers range from 130 to 214? Hopefully you guys can read that says 130. Looks almost like it said 120, didn't it? I'll fix that quick. All right, 130. Oh, in blue even? Come on. All right. I was ready for the next part. Oh, and then it looks bad. All right, you guys, this is going to be the last example we do. I don't know why this is not going so well for me. There we go, 130. Whew, there's part A, creating our normal curve. Then B, C, and D will just be related to those values and then the percentages on the front side. What percentage of women have a cholesterol reading less than 158? That would mean anything from 158 below. So looking at the columns that are generated from that, from 144 to 158, that's 13.6. From 144 to 130, there's your 2.2. And then don't forget below 130, that's that 0.1%. The percentage of women with cholesterol readings less than 158 is about 15.9%. And the label for that, or the label for the cholesterol reading, milligrams per deciliter, we don't have to put that in our percentage answer. And then it says for part C, what percentage or about 1% of women have readings between 158 and 186? So now if we're looking at our table between 158 and 186, that would be in between like one side or one standard deviation away from the average. So that would be where our 34.1 percentages are. Again, yep, this is our last example. 34.1% plus another 34.1%. Now this is the biggest part of the curve. It should seem reasonable that this is a pretty high percentage of values. So all the blood cholesterol scores or blood cholesterol readings, between 158 and 186 are approximately 68.2% of all the scores or data points within this distribution. The last example says readings higher than 200 are considered unsafe. So that would be too high of a cholesterol reading. About what percentage of women have an unsafe cholesterol reading? So that would mean what percent are greater than 200. So we'll say greater than 200. If we look over here, luckily it's a very small percentage. That would simply be that 2.2 and then that 0.1. So approximately 2.3% of all those data readings are in that unsafe category. Now the question remains, what would happen if you're somewhere in between those values? Like instead of 200, what if we said 195? Or instead of 158, what if we said 148? Well, the bottom is a z-score rule, and that's going to help us determine data values that are in between those standard deviations. And that's it for today. We'll call this good.